What happens when we have an RC connection on the output side? That is, we have a C filter and R load. Again, we know that the diodes that can conduct in the bridge rectifier when the source voltage is positive are D1 and D2, and the diodes that can conduct in the negative half are D3 and D4. That is fixed. But D1 and D2 can conduct only if the source voltage is more than the capacitor voltage, or if we assume that D1 and D2 are off, as long as the source voltage is less than the capacitor voltage or the output voltage, our assumption will be correct. So let us assume that the diodes start conducting, the diodes D1 and D2 start conducting at an angle delta after the positive zero crossing of input voltage Vs. We will know how to calculate delta soon, and that is the point at which the delta is the point at which Vs, the source voltage, becomes equal to the capacitor voltage. Now the diodes start conducting. So when D1 and D2 start conducting, Vs will be equal to Vo, the output voltage, that means the voltage across these two terminals is same as the input voltage. So the output voltage follows a sinusoid which is exactly the same as the input voltage. And how long the diodes D1 and D2 conduct? They conduct as long as the current is positive, the current through them is positive, or the current here is positive. And let us say that happens at an angle gamma after the peak of the sine wave. So gamma is the angle between the instant of diode turn off, or here the diode turn off of two diodes D1 and D2, and the peak of the sine wave. So how do we determine gamma? We have explained already in the case of half wave rectifier. Gamma is tan inverse 1 by omega RC. As soon as the diodes stop conducting, see, the current has gone to 0, and what happens to the voltage, output voltage Vo? It is the voltage across the capacitor, and the voltage starts falling exponentially like this. This is exponential fall, because what we have is just an RC circuit and this side is open because none of the diodes are conducting. So we are in the exponential fall interval. The circuit looks like this. But when does this stop? This exponential fall stopped at 2 pi plus delta in the case of a half wave rectifier as shown here, because in the negative half cycle we don't have any possibility of diode conducting. Why? The voltage of the source is definitely less than that across the capacitor. So no, the diode cannot conduct in the negative half. So the exponential fall continues all along the negative half cycle. But here we have two diodes that can conduct in the negative half cycle. Which are those two diodes? D3 and D4. We have two diodes that can conduct. And when can they conduct? They can conduct when the voltage VBA, because when D3 is conducting, this point is B, and when D4 is conducting, this point is A. So when VBA is more than the capacitor voltage, or again if you assume that D3 and D4 are off in the negative half cycle, that will be true as long as VBA is less than the capacitor voltage VO. But as soon as VBA becomes equal to VO, that means minus Vs becomes equal to VO, D3 and D4 should start conducting. So that instant is here. This is pi plus delta now. So the diodes D3 and D4 start conducting at pi plus delta. Once again, the output voltage VO follows a sinusoid. This is a flipped version of input voltage. And again, when does the current conduction through diodes D3 and D4 stop? It stops again at 3 pi by 2 plus gamma at an angle after the negative peak of input voltage. So that is 3 pi by 2 plus gamma. And when both diodes are off, D3 and D4 are off, obviously we enter again the same circuit in which just an RC is present. So the exponential fall starts happening. And when does the exponential fall stop? Again, in the positive half cycle of input voltage, where there is a possibility of D1 and D2 conducting. And when will they turn on? They will turn on at 2 pi plus delta, when the voltage across A and B becomes equal to the voltage across capacitor. Let us look at the transient condition also, where the initial condition on output voltage is 0. When the capacitor voltage is 0, initially the diodes start conducting right at the zero crossing, positive zero crossing of input voltage. Now the diodes will continue to conduct. In the very first half cycle, they will conduct all the way from 0 to pi by 2 plus gamma. This is pi by 2 plus gamma, just a little after the peak. Then the exponential fall starts and D3 and D4 start conducting at this point. So the output voltage becomes again equal to the input voltage, which is increasing. And then after 3 pi by 2 plus gamma, the diodes will stop conducting again, D3, D4. So the output voltage will fall exponentially to some minimum value. This minimum value is the value on sine waveform, which is equal to the exponential fall value. Then the diodes D1, D2 start conducting again, and the cycle repeats. So in the very first half cycle, diodes conduct for a very long time, but then once the periodic steady state is reached, the conduction time of diodes will be very short, which is determined by delta and gamma. So we have shown waveforms in periodic steady state in the slides. The average output voltage VO average can be found by integrating the sine wave plus the exponential fall interval appropriately, as explained in the case of half wave rectifier. So we first find the instant gamma, and then from gamma we have an iterative solution to arrive at delta, and using gamma and delta we can obtain an expression for VO average, which is given here. So the expression is quite similar to that in the case of half wave rectifier, where the difference is only in the denominator. So the denominator is 2 pi in the case of half wave rectifier, whereas it is pi in the case of full wave rectifier. Of course, we can always approximate this by the average voltage by Vm plus Vn by 2, assuming these segments, the segments of voltage as linear, which is a very simple approximation. And what is the minimum value of output voltage Vn? Vn is equal to Vm sin delta. And how about the source current drawn from the AC source? For that, we need to look at the current flowing in this branch. And how does it look like? The current flowing in this branch will look like this. In fact, current flows in that branch only when any of the diode is conducting. If none of the diodes are conducting, then the current through this branch is 0. So that gets kind of unfolded and appears as this waveform at the input. So that is what is shown by the green color waveform on the bottom right. So the source current is again having 0 average value, but then it will have a peak value IP In fact, it is non-zero only for a short duration, whereas it is 0 for the remaining duration. And as the value of capacitance increases, this peak value also increases. And how do you determine this peak value? It is given by this expression, Ip is equal to Vm by R sin delta plus omega c Vm cos delta, as we have done in the case of half wave rectifier.